My name is Yury Habets, and I'm an engineer at Unity. Together with Ben Clark from ARM, we are going to talk today about mobile performance and using ARM Neon instruction set with the Unity Burst compiler. Before we start, I'd like to briefly outline our today's talk goal. First of all, we are going to focus on CPU performance. GPU is out of scope for now. We want you, the creators, to do everything you expect and meet the frame time deadlines. And once you cope with that task, further improvements may reduce the energy consumption, which is really great for everyone. We're going to target ARM platforms today, and I mean Android, which I have the honor to work on for quite a few years. Unity Burst compiler is the core part of the talk today. And we are going to do a small dive into ARM assembly. But don't be too scared right away. We will explain things so we don't expect you to be a hardcore awesome professional. I hope we don't need to introduce how ARM and Unity are, but I wanted to say that we partnered together to improve performance on the billions of mobile devices that make up the Android ecosystem. During the recent years of our partnership, we accomplished a lot in the areas of performance improvements, tooling, and quality. Since I'm talking on behalf of the compiler track of the partnership today, a core feature we're happy to present are C# Neon intrinsics. But before we proceed with the intrinsics, let me do a brief introduction of what the Unity Burst compiler is. Burst is a compiler technology that converts your C# code in a form of .NET bytecode to highly optimized native code using LLVM backend. Burst is a part of Unity. It is not a general-purpose standalone compiler. And Burst is a part of the performance by default principle, making your C# code run blazingly fast with minimal effort. To show you the benefits that Burst compiler is bringing to your project, I'd like to demonstrate the video we showed last year in our joint talks with our friends from ARM. It's a demo with 3 playgrounds using Unity Physics, has 2 versions, one with Burst enabled, another with Burst disabled, and it runs on an Android phone. You can see it on the video side by side for easier comparison. The phone is in a thermal condition that is very close in the both parts of the demo, in a cool down state with no throttling after some 5 minutes of rest. So you can see that the difference in the frame time is at least 2x, with Burst being faster, obviously. And please make note that quite some rendering is happening here, which is not CPU heavy. In a thermally throttled state, the difference stays about the same, but I must say that it takes much longer for the bursted demo to make a device to start to throttle. As you can see, in some scenes, the difference comes up to 4x. That's outstanding results, which makes for an easy win to adopt Burst in your game. The performance of bursted output code is enough to satisfy 99% of our users. However, if you are within the remaining 1% who are still unhappy with the results and want to squeeze every extra CPU cycle out of your code, then we have a solution for you, and it is C# Neon intrinsics. Neon intrinsics are a way to write assembly code without actually writing assembly code. It has one-to-one mapping of the APIs to CPU instructions, but there is no need for taking care of non-exciting things like register allocation, ABI, function calls, integration, and so on. The C# API is very similar to C API for easier use. And the ARM V8 intrinsics are available in Burst 1.5, released in spring 2021. So you are free to check it out right now. Support for more intrinsics, including ARM V8.2 extension, will be released later this year. Okay, enough of theory. Now let's jump onto the practical part. Let's start with something really simple like a dot product. Here is a small snippet of code I've written for you. It is a function which takes two arrays of shorts as an input, and it accumulates the dot product in an integer variable. Please don't pay attention to the trials outer loop here. It is there just to make sure the calculation takes at least some measurable time. Now, let's write a C# intrinsics implementation. If you have any experience with C intrinsics, you immediately see that it's familiar to you because the API is very similar. Even if you look at the syntax itself, it's almost like C, with probably var being one of the few exceptions. If you replace it with auto, you can even try compiling it as C code. But okay, C++ code, but still the C# API is designed to match the C version. Let's take a look at this main loop here. You can see two loads from the input arrays into vector registers. Then come the long multiply and accumulate instruction here. And finally, we advance the pointer further for the next iteration. You can process 4 elements in a single loop iteration. So it's really classics of CMD. If the number of iterations is not a multiple of 4, then we have to process the so-called tail. You immediately see that there is more code here than in the managed version. Let's build it onto an Android device and check the results. What do we see here? Managed result is there for reference. It's an IALTO CPP build, so it's native code that has gone through Clang. It's not really mono-JIT, and it takes 387 milliseconds. Bursted version takes 82 milliseconds to complete, while the near intrinsics version takes 119 milliseconds. The reference device here and further is Samsung Galaxy S21, the European version with Exynos CPU, and the code is run single-threaded on the largest core, which is Cortex X1. So we see that the handwritten routine using near intrinsics is in fact slower than the code generated by Burst compiler. Why is that happening? Let's check the assembly in the Burst inspector. If you are not familiar with the Burst inspector, I highly recommend it to you as an ultimate diagnostics tool, which helps you check the assembly output for each of your bursted functions without having to build anything. Another cool feature is matching of C# source lines to assembly. Here you can see the assembly for the Neon code on the top and the assembly for the managed version of the code that went through the Burst compiler on the bottom. Let's take a closer look at the Neon version. You see the two load instructions equivalent to the two load APIs in the intrinsics, and the long multiply accumulate instruction, which also matches the code. So the instructions exactly match the code written in the intrinsics, and it is what we expected to see. What is Burst compiler doing then? The Burst compiler is auto-vectorizing the code, and it's doing it smarter than a simple Neon intrinsics implementation because the loops are unrolled. What it means is that you have the loads and two calculation instructions in a loop. So one iteration processes 8 elements instead of 4. To understand why the bursted code is faster, let's take a look at what the CPU is capable of. Here is a screenshot from Cortex X1 software optimization guide taken from developer.arm.com. Here are the load instruction variants used in the assembly above. As you can see, they have the same latency and the same throughput, but LDP loads 2 registers, so it's immediately more efficient. Assemblal allows for 2 instructions per cycle issue with a 4-cycle latency, but there is an accumulator fast path for integers which allows for a 1-cycle latency. Yes, it's quite a hard job even with this data to understand how many cycles the loop will take on the CPU. The branch predictor is likely to load the pipelines with more than just one cycle iteration, so the current one and the following one. But it apparently looks like issuing more instructions results in better performance. If we were using an advanced CPU emulator, we could get a very accurate insight into what is happening. But since we are not, I'm going to remind you that measuring is the fundamental part of any optimization. Okay, lesson learned. Handwriting simple neon code doesn't necessarily mean that it will perform better than what Burst generates for you by default. One of the reasons for that is that Burst did loop unrolling because it knew that the architecture of the modern CPUs allows for parallel execution, so it can handle more loads and more calculations at the same time. Let's try to beat the Burst compiler this time. And here are the suggested options. First of all, let's try unrolling the loops even more than Burst has done. And we will take it 3 wide, 4 wide, and 6 wide. Then let's use smlal2, which is a complementary instruction to smlal and operates on the upper half of the vector. I'm going to explain it in detail a bit later. Then let's try using smlal2 and do some unrolling. All the code is available on GitHub. I'm not putting it here on the slides because it doesn't fit well onto a single slide. Instead, let's dive into the Burst inspector assembly. This is one of the variants with more unrolling. In this case, it's 4 wide. 3 wide and 6 wide variants are pretty much similar. What you can see here in the assembly are 4 loads and 4 calculation instructions, allowing you to process 16 elements in a single loop iteration. This is my favorite assembly variant, short and elegant. It makes use of smlal and smlal2 instructions. First, it loads into Q2 and Q3 registers, which is the same as CMD V2 and V3 128-bit registers. And then come the calculations. The smlal variant we were using is taking 4 shorts in the lower half of the 128-bit vector register as each input argument, and it returns 4 ends in a 128-bit register as a result. However, if we load 128 bits from the input arrays, then we can use smlal2 instruction with the same V2 and V3 registers as input, but calculate the upper half of the vector. This way, we can use loaded data even more efficiently and not ignore the upper 64 bits loaded anyway. Next variant is similar to the previous smlal2, but it is 2 wide unrolled. First change is that it is using LDP load instructions, which load 2 Q registers at the same time from consequent memory address. Secondly, it uses 4 calculation instructions per iteration, allowing, once again, for 16 elements processed with a single loop iteration. Let's check the manual once again. In addition to the instructions you have already seen, I'm adding LDP Q form here, which loads 2 128-bit registers at once, and it has the same latency as the other load instructions, but only at a half of the throughput. So we're able to have 256 bits of data loaded after 6 CPU cycles, and it looks like it's the fastest we can get on loads. Now let's run on Android device and see what we can get. Great! The more unrolled variants are at least as performant as bursted code, and that's really great. I tried it out on a few phones, and I must say the performance of the unrolled options varies from device to device. For example, the 3x unrolled version, which is a bit faster here, was significantly slower on another modern phone. So use it with caution. The short and elegant smlal2 variant has about the same performance, and the 2 wide unrolled smlal2 variant takes only 66 milliseconds to complete. It is about 20% faster than what Burst has to offer. Fantastic. Okay, so we just realized that Burst is doing a really great job. We've written 7 new intrinsics implementation variants in C#, and one of them was 20% faster than bursted code. Great result. However, the remaining 6 had performance same as Burst or even worse, so some effort and experience is needed to write efficient Neon code, even for a simplest example. But the effort is worth it. 20% improvement on dot product is a great result brought by using C# Neon intrinsics. What I wanted to say is don't hesitate to consult the manuals to better understand what's going on. And of course, measure, measure, and measure again. Now on to Ben, who will look into a practical example a bit more complicated than just dot product.
Thanks, Yury. And indeed, we will see that getting Neon faster than the compiler first time is hard in my example too. But if you need that extra performance, then the effort can be worth it. Let's look at my example. My remit was looking for a realistic Android example, one that wasn't too complex, so the lessons could be general and learnt from. And the example should benefit from vectorization with Neon. Ideally, something game-like. Then I should see how much improvement I got from moving good code to Burst, and how much more performance I could squeeze out with Neon. I decided physics collisions would fit the bill if I made sure there were enough objects to test against each other. So I set up a scene to spawn lots of characters to randomly move about in a maze and test everything against everything. Our final trials used 2,400 characters and 236 walls. There are 2 different collision types within the project, giving me 2 different cases to optimize. Firstly, for characters being tested against walls, I use axis-aligned bounding boxes. And for testing characters against other characters, I test based on the radius and position of the 2 characters. And there are 3 different implementations of each to compare. For the control case, I start with good, tight logic, but don't use Burst. Then I wrap that in Burst, and then I convert to using Neon intrinsics within Burst. For references, there will be a document that covers a lot of the same material as this talk coming very soon on developer.arm.com. And the code and scene from this example is on the Unity Assets Store. Link is here. Here you can see the beautiful graphics from my scene. Sorry, as it's physics collisions, I just have the physics structures. There is no fancy rendering, just little capsules wandering aimlessly, bumping into things. The process where you add in Neon intrinsics to a script is going to be part of the measure optimize cycle, where you're trying to improve the performance of your game. You profile the game, identify the parts of the code that need better performance, where the CPU is doing too much work, and try to improve them. Profile again, see what difference you made, and go around the cycle again as many times as needed. You need to make sure you do your profiling on the target device. For Neon, you need to run on Android for it to work anyway. But in general, you'll get different timings as you use different tool chains for the build, different hardware, different optimization settings, etc. What is a gain in one isn't guaranteed to be a gain in another. The editor, in particular, while great for debugging, has minimal optimization, a different tool chain, and so on, so is pointless for profiling. Speedups there don't always translate to speedups in the final version. Burst jobs are great with their asynchronous nature being helpful in a multi-threaded game. So when I started my project, I used burst jobs, but I found they weren't easy for my measuring. I've since discovered that there are good tools that can be used alongside them. Profiler marker can be passed in to then be used with profiler recorder and/or profile analyzer to time within jobs. But as I wasn't making a game, so the asynchronous benefits of jobs weren't needed, and I wanted to display the timings on screen in my demo, I moved to a burst static function. Burst static functions are another great way to use Burst, but are a bit more restrictive with the parameters they take. Just simple types, pointers to simple types, and references to structs that just contain pointers to simple types. This meant I ended up moving to pointers and changing the layout of my data when I changed to a burst static function, which means the function isn't as nicely just burst wrapped to normal code and does probably make it easier for the compiler to auto-vectorize, but that's a good thing. Which brings us to look more at auto-vectorization. This is what makes Burst so good and what gives our handcrafted Neon a challenge. When targeting ARM64 as needed for Neon, you have to use Unity's IL2 CPP toolchain. This toolchain, after converting to C++, uses Clang to compile, and Clang is now very good at auto-vectorization to Neon. But Burst does even better than IL2 CPP. It understands your code better than a general purpose pipeline, so it can do more to make it efficient, including how it auto-vectorizes into Neon instructions. Easy performance gain. But there are things we can do in the code to help that auto-vectorization. Setting up our data and loops so that they are simpler to then turn into SIMD commands. I've got a short list of useful rules here, but to take you through an example, looking at this radius-based collision detection code, for data, x, y, and radius are split up and treated separately, which allows each of them to be vectorized more easily. For loop structure, there are two short for loops with simple addressing, no indirection, no breaks in the loops, and it has an inline function. Lastly, I cannot stress the importance of the no alias attribute enough to let the compiler know that the data the pointers point to is not overlapping. We struggled as to why Burst wasn't doing a good enough job until this was spotted. This small change meant it suddenly auto-vectorized and resulted in the radius code running in 1/3 the time it was, and the axis-aligned bounding box code running in 1/4 the time. Suddenly, Burst was faster than some of my Neon, and I had to tune it some more. So, you've got your Burst implemented, and you can see in the Burst inspector that it auto-vectorizes. What if it's still not efficient enough? Well, then we can look to write our own Neon. Likely, this involves some loop unrolling, hence the title. But what do we need to look at when we go to make our own efficient Neon intrinsics calls? Once again, data structure is important, as it is for auto-vectorization. Here, as you write the intrinsics yourself, you may get more ideas of what structure works best, so tweak as needed. Then, you have three phases. First, load efficiently into the Neon structures. Likely it involves a VLD vector load function. Secondly, keep the data in vectors as long as possible. Don't go in and out of Neon. Work out doing all the processing on multiple data rather than going back to single items. Thirdly, you want to store it efficiently. Unfortunately, the VST vector store functions didn't make it into Burst 1.5, but Yury's got them in as experimental in 1.6, so they're coming. In the meantime, there are some pointer tricks to get things out efficiently, and I advise looking at the demo code for what's been done to extract as well as possible. The change in how I got the data out made quite a difference to performance, so it is important. Let's look at each of the two subcases to go through the important improvements, starting with the simpler one, radius-based collision detection. Firstly, as before, we split the X, Y, and radius for processing separately, so they're each able to have 4 loaded into a vector at once. Now, Neon code is quite long, especially the tail code, the less vectorized parts left at the end. So this is just a clip of the code on the slide, just the main inner loop. To see the full implementation, please get the example scene from the Unity Asset Store. So here we have one character already loaded in to compare against, and we loop through the other characters. We load 2 lots of 4 more characters at once, so we can do the comparison with 4 32-bit floats, but then compress the answers to 8-bit values, and then extract all 8 results at once into our Boolean array of collisions. This float to Boolean conversion is slightly easier in C# than C Neon intrinsics, with Unity making good use of the dynamic typing to help us. The logic of the collision detection is exactly the same as in the burst back here, albeit a lot longer, as the x subtraction, y subtraction, result squaring, adding, and comparing to the squared radius are now all separate lines. We're just explicitly loading and comparing 4 at once, doing it again with another 4, and then squashing all the results with a table lookup into a shorter 64-bit vector so it's ready for extraction. As mentioned, we also have to cope with tailcode, as the unrolling uses a multiple of 8. We aren't guaranteed our number of characters will be a multiple of 8. So there is firstly tailcode to cope if there's another 4 more, essentially similar to the first half of this, but with a slightly different extraction to get 4. And then more tailcode for if there's fewer than 4 comparisons left for the character. I still load 4 in and calculate and redo some results because it'll be faster than doing on average 2 singly. The more complicated case was the axis-aligned bounding box collisions. Here, there was more potential to lay out the data well for Neon and get a bigger advantage. As implemented in the original non-burst code, our best way to check for a collision is to check that the bounding boxes are not missing each other on each axis. If the maximum value of one is less than the minimum value of the other, then it's a miss. Repeat for both sides and each axis. If there are no misses, then it's a collision. But we can set up the data so that all the checks for a 2D collision can be one greater than check, with Neon doing all 4 checks in one command. For the first go, we do this, then OR the answers in another command and negate it to get the result, which gets some impressive performance and needs no tailcode, but we can do better. We can unroll our loop and do 4 walls at once. We do each of the checks for 4 walls and then can combine our results, meaning our OR and NOT do 4 walls as well, instead of 1 in the first version. And then we can do even better by doing the same extraction technique we did with the radius and doing 2 groups of 4 and then combining. Our NOT is now on 8 walls at once and extracting all the results in one go. Initially, I did the compression from 32-bit values to 8-bit ones with some bit shifts, but a table lookup allows it to be done in 2 instructions instead of 3, making a small further saving. As one final addition, we can remove some tailcode as our final test has a guaranteed number of walls. It's a multiple of 4, but not 8, so I just handle the case of the last 4 walls at the end. To have a quick look at the code snippet here, we load the character's 4 bounding box limits with VDUPs to put the same value into the vector 4 times, ready for comparison with 4 different walls. Then for each set of 8 walls, we handle 4 at a time and load 4 walls into each of 4 arrays representing each bound of the box. Then we're comparing the max of one to the min of another. Half the bounds are negated so that they all end up as greater thans. Not strictly needed in this final implementation, we could have less thans, but no slower either, as the negation is done once at data setup when loading. Grooming the data setup like this can be important to your efficiency. The results of the 4 arrays are ORed together, giving us 4 collision results. They are then put into one end of a vector, ready for the next 4 results to be put into the other. Not seen here, those next 4 walls having been put in the other end, the whole lot is negated and extracted with a pointer cast, like the radius-based collision detection code we just saw. Which brings us to our results. These are on a Samsung Galaxy S10 Plus, but a quick test on the S21 gave similar results. As you can see, Burst's auto-vectorization gives us some big speedups, especially for the axis-aligned bounding box case. Here, it's running the collision tests in approximately 1/6 of the time that our tight, non-burst implementation takes. Neon intrinsics allow us to shave off a further 40% of the time remaining. For radius-based, it's a simpler calculation and harder to get as much speed up, but still, the burst implementation takes a little over 1/3 of the time of our original implementation, and Neon takes off another 20%. So, these are some big gains. Burst gives us a big speed up without the effort of handcrafting Neon and the harder to read code. but if it's important and you need that extra bit of performance on Android, you can squeeze out some more with the Neon intrinsics. So, to summarize, Burst is performance by default, easy to turn on for sections of your code, and it gives a big speed up with a lot of auto-vectorization. For 99% of users, this is all that's needed. But if you need to squeeze out more on Android, you now have the C# Neon intrinsics. Here you can fine-tune performance and get even better results. But to get those better results, you'll have to work hard to beat the compiler. So pick your battles of where you can get the performance gain for the time you spend implementing. As ever, when going for performance, profile to find where you can get your gains. Hopefully, the tips we've gone through on data layout and loop unrolling will help you get that ultra efficient code you're looking for. We look forward to seeing that high performance code in your new games. From Yury and me, thank you.